Been a long time since I posted a video on mathematics. Alright. This is upon one of the requests from one of my students. This question is pretty interesting though. Okay, let's try to solve it. Right? Now the questions is find the sum of squares or roots of the equation x cubed plus x plus 12 equals 0, and deduce that only one of the roots is real. Now that's the first part of the question. Okay, now once we are able to prove that, then we will continue with the second section. The real root of the equation is denoted by alpha. Prove that this real root lying between -2 and -3, and then therefore or hence prove that the modulus of each of the other roots lies between 2 and square root of 6. Okay, now let's look at how to go about this. Okay, now first of all, we are given this cubic equation. All right, now using the properties of roots, we can deduce that, or better still, to be safe, we rewrite in this format. It will be much more easier, no? Yeah, I think this one will be much more easier. Here we can recognize all the coefficients for each one of the expression, x cubed, x squared, x, and its constant here. Let's denote all the solutions or the roots for this equation as roots for equation 1 as alpha, beta, and gamma. This is a typical symbol that we use to denote all the roots for this equation. Now therefore, by using properties of the polynomial equation, we can deduce that the sum of roots is equal to 0. That will be one of the property. And then next, we also know that the sum of the products, which is alpha, beta, alpha, gamma, and beta, gamma, as -1. That will be our next property. Let's call this property A, B, and then we also have another property regarding the product of all its roots, which is this one here. Here we have a -2. Is it a negative? Negative, positive. Oh, sorry. I think I made a mistake here. This one is supposed to be positive. This one is negative. So now these are all the non-properties of polynomial. Other than that, we can also deduce an extra property, which is intrinsic to this equation here. So knowing that, or by assuming that alpha is actually one of its root, then we can directly conclude that alpha cubed plus alpha plus 12 is actually equal to 0. This is the extra property that we can have. Whether we need all of these properties to work out or to deduce the first section, we're going to check. Right? All right. Now let's look at how to make use of. From my perspective, I would say I only need either one or two of these properties to be able to deduce that one of the roots is real. There's only one root which is real, which means the rest must be complex roots there, right? And then by using the property of polynomial, knowing that the coefficients for this polynomial are all real, therefore we can deduce that um, we can have, in general, all the roots are typically can be complex by nature, right? Complex by nature. If we have two roots that are complex, therefore usually these two roots will come in the form of uh, complement roots. Okay, by complementary roots, I mean that if if both the roots are complementary, then we can say that now let's assume that beta and gamma are complex. So if these two are complex roots, usually they come in the form of complementary to each other. Therefore, if beta is denoted as a plus ib, where a and b are all uh, integers numbers in this case, then therefore we can deduce that gamma will be its complement or its conjugate in this case, where the a and b are all integers. So if these are complex roots, then they always come in the form of conjugates. Okay, now that is what we understand, right? What we know of, right? Okay, now before we can come to these sections, we have to see whether we will be getting a complex roots. Now, if we do, then in general, the roots will come in pair of conjugates. Now, first of all, we are going to use the property of, before that, we're going to find the sum of squares of the roots. Let's see whether that is helpful to us in this case. So the sum of the square would be alpha square plus this, which is generally the same as this one here. Let me see, that will be, yep, correct. So that will be alpha beta plus alpha gamma plus beta gamma. That's what we have. So by using all the property A, B, C here, we should be able to obtain the numerical value for the sum of square of the roots. So sum of square of the roots, we have the sum of product, which is a 1 here. And then we have the sum of all the roots, which is 0. So that will be 0 square minus 2, 1, which we end up with a negative 2. So here we can write down alpha square plus beta square plus gamma square as negative 2. Alright, so we have managed to find the sum of squares of the roots here, right? Which is negative 2. Right. Now generally if alpha, beta and gamma are all real, okay, let's assume that they are all real, then therefore it is pretty straightforward that this the sum of square of all these real roots must be greater than or equal to 0. But these conditions here contradict with these sections here. contradict with this finding that we have, which is negative 2. Therefore, we can, therefore we must conclude that not all the roots are real. Not all the roots are real. And then knowing that if there is a complex root or roots, they must come in pair. Because of this, we can say that there must be two complex roots that are conjugates to each other. Okay, and then because of that, we can accept this understanding here. We can say that since we are pretty confident that two of these roots, let's make assumption, this is just my assumptions, let's assume that these two are the complex roots. Therefore, we can write in the general complex numbers format for beta and gamma, which always come in a pair of conjugates to each other. Okay, all right. So that is how we deduce that only one of the roots is real. So since both of these must be complex conjugates, then it only left us with one alpha, which must be real though. Okay, now I'm going to show you why would I conclude that beta and gamma must be conjugates to each other, and then why alpha must be the only real roots. Can alpha be a complex roots or not? Yeah, you must be wondering. Okay, now let's try to prove it simply. All right, I'm not using any rigorous proof here, so I'll just use a very simple case by case observation. Right, now let's assume that. Let's assume. Sorry, I made a mistake here. Sorry about that. Let's assume that. Let's assume that alpha. Okay, alpha is real. Okay, alpha is real, whereby beta and gamma are all complex. Okay, are all complex, right? Therefore, we can write we can rewrite this statement here. We can rewrite the statements, the double star statement, as okay. We can rewrite as alpha square plus a plus ib square plus a minus ib square here. Now let's try to observe this case one here. So from here we found out that we have alpha square and then plus a square. So we can see that this is pretty much a square, and then eventually you get a minus b square here, and then this one is also a square, and then eventually you get minus b square. So that is basically just a b square. I hope I did that correctly. Alright, let me check one more round. That is 2ab, this is minus 2ab, so they cancel each other. And then this is plus I square. So don't forget I square is actually negative 1. So this is what we end up with. And then you can see that all these are real. A is real, B is real, alpha is also real. Therefore, the whole summations will produce real numbers. But these real numbers may not always be greater than 0 as what we expected because of complex number, because of the existence of complex number. If there's no complex number involved, then it's impossible for us to obtain these particular conclusions here. Therefore, that's the reason why we have to take into consideration there must be a pair of conjugates complex between alpha, beta, and gamma. Okay, right? That actually prove the case one. The reason as to why two of these roots must be complex conjugates to each other. Right? Now, can alpha be a complex number or not? That will be another questions you may like to know, no? Okay, if we assume alpha, beta, and gamma to be complex numbers. Okay, if we assume such a case, therefore we can rewrite that statements one more time. So from here we will get like yeah, okay. Since both the beta and gamma are complex conjugates to each other, I will be using a different symbol to denote the complex number for alpha. Then I'll just call that P plus IQ. Then this one will be represented the alpha, and then these two complex number will still stay the same as 2a square b square here. And then eventually we will know that here we will get p square minus q square plus 2a square minus b square, which are all real. And then we have 2pqi. So you can see that if we assume all of them are complex numbers, therefore it's impossible we will arrive to this conclusion, whereby we only have an integer number as the sum of square here. Right? So this is a contradiction. Therefore, the only possible solutions that we can have here in order for us to get -2 is we must have a pair of complex conjugates with one real roots. Now that would be the best deductions for as to why there can only be one real roots, and then the other two must be a complex conjugates. So I hope that this very simple case-by-case observations will give you an idea as to why we only have one real roots, and the other two must be a complex conjugates. All right, so that's the first sections, 4 marks though, but it takes us a long time to go through the reasoning or the deduction itself. Alright, next I'm going to make use of all the result that we have for the first sections that we have deduced to answer the second sections. But the second section is much more easier to deduce in this case. Alright, now before that, let me erase off all this that we don't need at this point. But I do need to make a remark here. I will copy down what we have is the sum of square, which is alpha square plus beta square plus gamma square is actually equal to -2. That is our finding from the first sections. We might need that in a while. And then we will be using this general form to denote beta and gamma. Alright. Now next, how are we going to prove that the real root alpha actually lie in between here? Right. Now, as I said, from property that we have deduced D from property D here, we can actually write down alpha cube plus alpha plus 12 equal to 0 there, right? Now, if alpha is lying between here, it means that there must be a change of sign to these particular functions. All right. Now, before that, let's denote f alpha as alpha cube plus alpha plus 12 as a general function, right? As a general function. So now to give you a visual understanding of what we are trying to do here would be, now because it's a cubic equation and then alpha is real roots, so most probably it's going to give us an indications of how that graph would typically look like. So I'm just making an assumption, so it might look something like this, for instance. Yeah. Because that's the only real roots that we have, and then they are they are actually asking us to prove that these particular roots, this is the root that we are interested in, actually lying in between -3 and -2. Sorry about my drawing; it's not to scale here. Right. So let me label this correctly. Right. So as you can see here, the actual root is lying between -3 and -2. How can we actually prove that? Now visually we can see that um, anything 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 on the left hand side of the root will have a, a sign, a negative sign, I would say. Negative sign uh, with respect to its own function because it's below the x-axis. If I try to test the sign for the right hand side of the root, then most probably I'm going to get a positive sign here. So you can see that if the root is lying between here, there must be a change of sign, or else this will not be a root. This will not be a root. Okay. Now take for instance this one section here. Can I say that the roots actually lying between -3 and 2 then for these particular sections? Yeah, I cannot. First of all, because the sign for this whole section here is all positive. You can see that it's all positive because the graph is increasing all the way. There is no chance that this graph would actually dive down to the negative sections here. So we're going to use that a very basic understanding of change of sign to test whether the actual root, the actual real root, actually lying between -3 and -2. Now to do that, all I need to do is this. So I'm going to put in -3. Right now, -3 here, -3 plus 12. And then this is -27 here, and then you have -30 here. All right, now that is pretty obvious. I don't really need to work out the actual numerical numbers for that. It must be less than 0. And then I'm going to test out for -2 though, which is -2 to about 3, -2 plus 12 here. Now that is actually a -8, -10. Now that is actually a 2, which is more than a 0. Yes, we can see that there is a sign change. This is negative sign. This is positive sign. Therefore, we can deduce that alpha must be lying between -3 and -2. Right. Now that will provide us with a very simple proof as to why the real roots alpha will be lying between -3 and -2. Okay, I hope that is clear to all of you. Right, now, finally, the last part require a bit of your understanding of complex numbers and their complex conjugates. Okay, now I'm going to erase off these various sections here since we have done this already. Now, a bit of recap on the complex conjugates though. Now, since we made assumptions that beta gamma is a complex conjugate, therefore I'm going to write down some of the properties that we know of. Now, let's try it out. So beta multiply gamma. Let's give it a try. If you can't recall this, that's fine. We can do an experiment on this and then figure out the properties along the way. Based on the same notations here, we're going to write down a plus ib, a minus ib here. And then that will automatically give us a squared plus b squared. That's very obvious. And then the interesting part about this is here. The modulus or the magnitude of this complex number is this one. The magnitude of this is actually let me see. The magnitude of beta is a squared plus b squared, as we know. And then this magnitude is also the same, also having the same magnitude as gamma, since they are complex conjugates to each other. So we have plus b squared also. Even though there's negative there, this is a square, so you should have a positive. So from here we can say that since they are complex conjugates, both of this magnitude must be the same. No? Must be the same as a squared plus b squared. That's pretty obvious from here. Alright, now we're going to make use of these extra properties to help us to prove that the modulus of each of the other roots lie between 2 and square root of 6. Okay, how am I going to do this? I'm going to make use of this very little result that we have proven just now. Okay, and this one here, and property C. Okay, so using alpha more than -3, less than -2, and property C here. Right? Using both of these, we're going to deduce the modulus. All right. Now, how are we going to do that? Okay, let me try this out. So we have alpha, beta, gamma equal to -12. So from here, we can state that alpha is actually -12 over beta gamma. And then we know that beta multiplied with gamma, which is exactly the same as the magnitude of the complex number itself, or the modulus of the complex number. So we can actually write down this as -12, this one, or we can write down -12 as this one, because both of them are the same. So let's choose one of these. We're going to substitute this into here, into this one here. So we will get -3 less than alpha, which is -12, beta less than -2. Right, now if you deduce it and simplify it, you will find that the modulus of this must be greater than a 4, less than a 6 is very obvious. You can work that out, shouldn't be a problem. And then, oh yeah, I think I made a mistake here. I forgot to put down, hold on. Let me correct that. This is the square root of that, so I forgot to do that. Let me correct that. That should be the square of the magnitude of this, should be equal to this. This is the square of the magnitude, and then therefore we can conclude that the square of this is actually equal to this. Right, now that's my mistake. I hope you're clear on this correction. Okay, and then here I'm also going to correct this. This one should be square now. Yeah, I think I forgot that. Okay, this is square. So this is actually a square. Yeah. All right. Luckily, I spotted the error. And then from there, we can conclude that the modulus of one of the root must be a 2 and root 6. Now, we can also say that the root gamma also lying between 2 and root 6. All right. I hope that would be a clear explanations to the solutions to this question. Yep. So bear in mind some of the common mistake that that I have done, and then most probably some of you may commit. So hopefully not. That's a good thing. I noticed my own error. I hope that you also notice this particular error, which is very important. It's actually the square of the modulus of each one of the complex number is a squared plus b squared. Because most of the time I hardly use the square root. That's the reason why I've forgotten the square root there. Right. So I hope that would clear your understanding on these questions there. Yeah. Okay, do leave a comment or anything if you feel that there's some corrections needed. Yeah, I'll try my best to correct them if there's any mistake to my solutions. Right. So I hope that you are clear on the explanations. Do yeah, do post up any other requests if you'd like me to um, make some explanations on the questions that you are interested in. Right. Thank you very much.